This video I will be discussing how to reconstruct a dataset through the LTT GUI. So here I have launched the GUI, and the first thing we're going to do is click Load SCT. So what I'm doing here is this is the way you would process data if the data was collected either at Livermore, which therefore it will have an SCT file, or through ALS at Berkeley. So they also save data with SCT files, and it's basically just a file of all the metadata. So we'll click Load SCT. Well, and before I continue, notice a few things I'm going to cancel. That you don't have to have an SCT to be able to process data. All it's going to do is populate all the necessary fields that you need to do the reconstruction. But if you don't have one, like if you had data that wasn't collected at Livermore, or ALS, then everything here in red you would have to fill out. So archive directory, that's where the data is stored. You'd have to type that in, or you could browse to the location. And then if you hover your mouse over it, here, it gives a tooltip. So it basically says what the parameter name is and a short description of what the parameter means. So you can hover over any parameter here, and it will tell you what it means. And so the way the GUI works is the top left window is the workflow window. This is why it's called LTT workflow. And you enter everything in, and then once you're done with the page, you click next. And you just keep doing next until you get to the end of the processing. And then this is the main image display window where you'll see your raw projections or your sinograms or your reconstructed slices. And then on the bottom left, there's a bunch of different windows. They're all tabbed behind each other. In a further video, I'll show you more detail about what all these do, and a little bit later in the video. But anyway, let's load our SCT file. So I'm going to go on here, click that. As you see, all the fields were populated, and we see an image of our projections. And I can go through the slider and look at all the projections here. So if you see an image, it basically means things were loaded correctly. So if I go to the next page, you see all these fields here were populated. If you want to see what the system looks like, this is the basic geometry, where the black is the detector, the source is here, the blue thing is the field of view. So this one has a big magnification factor, and this is a cone beam acquisition, as you can see. So this is good just to know you can see whether you set everything up correctly. Anyway, that's all fine. We'll go to the next page. And this is to set up your pre-processing queue. So the data is raw. We have to pre-process it in order for it to be ready for reconstruction. So the first thing we'll do is we'll click New Pre-Processing Sequence. And the first question it asks you is, you have two options. Do you want to process everything in RAM or in memory, or do you want to use the disk? If you collect in RAM, what it's going to do is, when the first algorithm is executed, it's going to load the data, all of it, into RAM, and then it's going to process the sequence of algorithms and never write anything to disk. If you use disk, then after every algorithm is run, it will write its result to disk. Now, if you don't have enough memory to process this data set, this in RAM box will be grayed out, so it won't even allow you to do it. You'll have to use the disk. So not using the disk is good because it doesn't take up a lot of memory on your hard disk, and also it'll run faster. So writing to disk is a slow process. Using the disk takes up more space, but the good thing about it is you have a full log of all the steps that you took in your processing. So if you want to rewind or go back to a certain step, rerun an algorithm, then use disk is really good for that. Anyway, we're just going to do the in-RAM processing for the demo today. And then next thing we do is we're going to add algorithms to this queue. So if I wanted to, I can add algorithms one by one. Here's a list of all the pre-processing algorithms. And they're sort of organized as follows. The first couple here are usually things that one would apply to the raw data. The next algorithms here are converting the raw data into either transmission or attenuation. And you'll need to do one of these algorithms to prepare the data for reconstruction. And then the next set of functions are usually done after the data is in attenuation space, and they're usually applied at that stage. And then the last set are sort of special purpose algorithms. But they're also ordered for you. I mean, you can do them in almost any order you want, but they're ordered this way to sort of show you what's the usual order that you would do things in. Anyway, I could add these one by one, but instead, I'm just going to click the default button. And this is what LTT suggests that you do at its basis. So the first thing it's going to do is make attenuation radiographs. This is subtract off the dark, divide by the background, take a negative log. The next one is outlier correction, which will remove like zingers or outliers or bad pixels. Next one, it finds the center pixel of rotation. You don't have to run this if you already knew what it was, but it's a good way to estimate it. And the last one is ring removal. And you'll see in all these algorithms you have buttons that say help, preview, and execute. The help button, just like the tooltips, brings up a full description of what the algorithm is doing. The preview button is available for most algorithms, and the point of it is that some of these algorithms may take a fair amount of time. So the preview button allows you to apply the algorithm on a two-dimensional subset of the three-dimensional data cube and immediately show you what the result will be. So this is good for parameter tuning and whatnot. And then the last button is execute, so it'll just run the whole algorithm. Now, as the algorithms are here, you can click and drag to reorder them. I can click remove or add, whatever I want. But let's run through, and one more thing. If I went down here and clicked execute, then LTT would look and say, well, you haven't run any of the algorithms before it. I think it, and so what it'll do is it'll run the algorithms all the ones that haven't been executed before it, and run this one. So I could do this right now, and it would finish the processing, and everything would look fine. But for demonstration purposes, I'll run them one at a time. So let's first take this one, make attenuation radiographs. So one thing that you can do in it is apply flux correction. And what this does is this will normalize out the view-to-view variability in flux. It's not necessary, but sometimes it can improve image quality. So let's do that. So to do that, you need to find a place in the beam that's never occluded by the object. So somewhere here on the edges. So it's hard to tell what that is because this object rotates around. So what you can do is say show stacked projection. I'll click that. And what it's doing now is it's reading all the projections off the disk, and in this case taking the minimum of all of them. And so you see the largest shadow that it makes. And now I'm going to click and drag a region of interest, and you see it's not a part of the part. It's just a region that will only see air. And if that box won't click for you, sometimes you'll have to go down to histogram down here at the bottom and click region of interest, ROI. That turns on the box. Anyway, after I have it where I want it, I say populate fields from ROI. When I click that, these four will update. They're updated. And now I'm ready. So I'll go ahead and click execute. And then it's done. And also what it does is, just for a diagnostic, is it showed you what the mean of that postage stamp region was in transmission space. So you see, actually it was a pretty stable source flux. The only thing that you would really have to look out for is if this value suddenly changed far from 1, then it would usually mean something happened to the source, like maybe it went down, or it could mean that, if it looks weird, it could mean that the region of interest that you identified actually did move over the part a little bit. Anyway, it all looks fine. I'll close that. Next, outlier correction. If I wanted to, I can mess with these parameters and click preview. Actually, I'll do it. You see that you can't see much that's changed, but it opened up it says down here, outlier correction preview. This was before the correction, after the correction. You see that this particular data set has no outlier, so it didn't really do anything. But we'll put it in there anyway in case there is, a pixel here and there that it corrects. But mainly outlier correction is just supposed to correct, fairly rare events. Okay, now we'll click Find Center and run it. And so this is going to go through all the data, try to find out where it thinks the center of rotation is. So first you can see it says it was running outlier correction. And also this one puts up a diagnostic plot. So it basically shows you the conjugate ray mean squared error versus the center column index. And all you're really looking for here, if you care, is a clear minimum, which it does have. So, in a very good high likelihood, this found the correct center of rotation. And it will find it less than a pixel in accuracy. It's very accurate. Well, most of the time. Okay, now let's go to ring removal. And ring removal is interesting. Once you do an algorithm, I'll click add, that's in this area right here, all of these algorithms, when you click the preview, they'll apply it to one sinogram. The ones before it applied it to one projection. Actually, it'll apply it, in this case, applies it to all the sinograms necessary to reconstruct a single slice. So it's going to apply it to those, set of slices, the ring removal, and then reconstruct one slice. And then, so here's our result. So it applied the ring removal and did a single slice reconstruction. And in all of these, I didn't mention this before, the preview, you can preview which slice you're interested in. So for this one, the default is in the center of the volume, but I could say maybe 100. That's slice 100. And then you get a different slice. For things like outlier correction, in the preview, you're entering the view number. Anyway, it looks fine to me. Let's just finish the execution. Okay, we're done. So at this stage, I can move on to reconstruction, but another thing I can do is, if I was fine with the whole process, I can go down to here, save projection data, and this would just save it to disk, just in case I wanted to redo the reconstruction. We don't need to do that. We'll move on. So the next page is the reconstruction volume. It's usually already populated for you, but you can change this as you please. If you hit this button, Restore Defaults, it gives you the default volume location, which is the volume that fills the field of view with the pixels sized sort of at the default setting that you want. This compress volume files, if you click this, it will compress your reconstruction into a 16-bit integer file instead of a 32-bit float. And then here you choose your ramp filter. You have a couple options between smooth, standard, sharp, ultra sharp. If you click custom, then you can give the full width half maximum of the ramp filter, and this is measured in full width half max. This is in pixels. So the standard here is just the Shep Logan Phantom. Okay, anyway, we didn't really have to do anything here. I was just telling you what it does. The next page is the reconstruction page. So here's all the reconstruction algorithms that are available to you through the GUI. Filtered Backprojection is the default. It's usually what people want. So I could say reconstruct volume and I would be done. But let's show you a few more things. Let's go to parameter tuning. So finding the center column is not always done perfectly by the find center algorithm. And it's really important that you get it right. So this provides you with a tool to help you estimate that better. So what we can do here is we could say I want the center column. This is the value currently. There's a lot of options here, but let's just do, I want to do 3 samples, 3 reconstructions. I'm going to try 3 reconstructions. Sample rate spaced 1 pixel apart. So this is going to do 3 reconstructions, one at 333.473, one at this value, one at 1 plus this value. So let's say reconstruct slice. And then here are the 3 reconstructions here. You can see, I hope, that the middle one here is a little sharper than the other 2. So you could probably say, yeah, that one's better. It does give you this metric that tries to help you say which one is the best. It provides a metric of the sharpness and of the entropy. You want to try to choose ones that maximize this. These things are helpful, but they're not always perfect. So if I want, based on this information, I could choose which one of these I liked best and say OK, and it will change my value. But anyway, I'm not totally convinced, so let's try a few other things. Another way to find out what the center of rotation is you can do a short scan reconstruction. So this will throw away a lot of the data until you're basically using only 180 degrees plus the fan angle. In these reconstructions, what you're looking for is like tuning fork artifacts that show you that your reconstruction is not perfectly aligned. But the one I like best is this inconsistency. So what this does, and this only works if you have at least 360-degree rotation CT data set, is it tries to reconstruct the inconsistency, meaning if it's perfectly aligned, all your reconstruction should just look like noise, no features. And so this one is really easy to see if you're even the slightest bit off. So let's run it and you can see what I mean. So now, here are the 3 reconstructions. You see that the one here obviously has very few features compared to the other 2, so it must be the one that's most aligned. It also provides you the L2 norm of these images, which is a form of error, and you want the one that's the lowest. So it's a pretty clear winner here. But let's make this harder. Instead of 1 pixel, let's do a half a pixel. So you're only going to shift a half a pixel of the current estimate on either side. We'll run that one. Again, it's very clear which one is the best estimate. Even the metric shows this. So you can see this method is really good for finding an accurate center of rotation. The other thing that it shows you is how that find center algorithm did a really good job at estimating this. Anyway, none of that was necessary. It was just to show you some of the tools. So let's go down to Filtered Backprojection and we'll reconstruct the whole volume. So keep in mind this reconstruction is about 600 by 600 by 600 in size, and it's running on my laptop. So this will take a little bit of time, but not too long. This was actually downsampled by a factor of 4, I think, from the original acquisition, just so I could show you, a reasonable timed demo of what's happening. Now, before, all the pre-processing algorithms that were run, they were not writing to disk. Whenever you run a reconstruction algorithm, it will always automatically write it to disk. Anyway, our reconstruction is done, and here is a z-slice. And if we go down here, we can go through all the z-slices of our object. We can also slice it in the y slices. Here, we can also do it in x slices, going this way. We can also oblique slice it, so these are slices not necessarily aligned with that axis. I'll talk about that later. And 3D allows you to do 3D renderings, which I'll also talk about that at a later time. One final note is this particular reconstruction has a lot of artifacts in it. And there are like these black spots here. So let's zoom in. Now these are artifacts here. And in a later video, I'll show you how to do a physics-based reconstruction that removes those artifacts. But here we're just showing you pretty much the standard routine of how things go. Now, that was all fine and good, but one more thing that I'd like to show you is that LTT really, the GUI here is really just running LTT in the background. If we bring up this, every command that we did, we could see the text coming from LTT. It includes, percentages done in the background. So if you have a long process, you may want to check this to see how far along it has gone. The other thing is when you're running an algorithm, the GUI will be frozen up. So they share the same threads. So when an LTT algorithm is running, don't click around the GUI. Just leave it alone, let it finish. But this is also showing you that I could have done all of this through an LTT script. So if you prefer scripting, so scripting is nice because it gives you great control over the processing. But if you like scripting, I would still recommend that you start off your first reconstructions using the GUI. And then what you can do is, we'll go back to the beginning here, click on the Preferences Miscellaneous button. And if you look here, Command History, Track History is automatically turned on. So if I say Save History, let's just put this here because I don't have much here. We can save all the commands for ourselves here. And then if I open that up, here's the commands. I can see here that if I run this script through the LTT console, this will do exactly what I just did. So you can see in the background all the commands and how the syntax works for how LTT works. So this is a good way to maybe do something once, and then all you'd have to do if you want to do batch processing is you just change here, this command, the load SCT. You just change which data set you're processing, and this will allow you to do things always identical. Okay, that's the end of this video. I think the next ones I'll show a few more advanced features. Thanks.